In this video, we'll use what we know about the trig functions sin x, cos x and tan x to define the functions f of x equals sin x, f of x equals cos x, and f of x equals tan x. You've probably seen how to define sin x using a circle diagram, and I'll just remind you how to do that. We draw an angle and a line at x degrees from the horizontal axis. So that line there is at x degrees from the horizontal, and then sin x is the vertical axis coordinate, so it's that value there on the vertical axis. So this here is sin x. And we can use this picture to see how changing x changes the value of sin x. When x equals 0, sin x is 0. As we increase x up to 90, where x is measured in degrees, sin x increases up to 1. As we increase x further, sin x decreases. It becomes 0 when x equals 180, and then continues to decrease. It becomes minus 1 when x is 270. After that, sin x increases and becomes 0 when x reaches 360. We have now come back to where we started on the circle. So as we increase x further, the cycle just repeats. We can also use this picture to see what happens when x is less than 0. Also, from this picture we can see that whatever value x takes, sin x must always be between minus 1 and 1. Now that we have an idea of how x and sin x are related, we can try to plot a graph of sin x. Let's work out some values for sin x first. Here I've got a table that's ready to be filled in with values for sin x. You can use your calculator to work out these values. I'll fill in the table now. We know that sin of 0 is 0. Using your calculator, you can see that sin of 45 is 0.71 to 2 decimal places. Sin of 90 is 1. Again, use your calculator to see that sin of 135 is 0.71. Sin of 180 is 0. Your calculator will tell you that sin of 225 is minus 0.71. Sin of 270 is minus 1. Sin of 315 with your calculator is minus 0.71. And sin of 360 finally is 0 again. Now what we can do is plot those values on a graph and then use our knowledge from the circle diagram to fill in the rest of the graph. And that's what I've done here. I've plotted sin of 45 and 90 and 135 and so on, and then filled in the rest of the graph from 0 to 360. Now our circle diagram told us that as we increased x up from 360, the cycle just repeated. So between 360 and 720, we just get another copy of the sine graph. And if we were to increase x further, we would just get the cycle repeating itself again. So this would carry on forever. Now, as we decrease x from 0, it was like going backwards around the circle. So from 0 down to minus 360, it just follows the same shape. And that would go on forever as well. Now, since this cycle repeats itself every 360 degrees, we can say that sine x equals sine x plus 360. We say that sine x is periodic with periodicity 360. Sometimes we want to work in radians instead of degrees. Sine x in radians is very different from sine x in degrees. Here's an example. We've seen that sine of 90 degrees is equal to 1. But sine of 90 in radians is about 0.894. Now here I have a table of values which shows x in degrees and then x in radians and the value of sine of x. I can also show you a graph of sine of x in radians. Again here we have the graph repeating itself 3 times. Now looking at this graph, it looks very, very similar to sine of x in degrees. But really you must remember that sine of x in degrees is a different function from sine of x in radians. And you can see this if I show you the 2 graphs plotted together. On this pair of axes, I have sine of x in degrees as the green line. Now x is going between 0 and just over 60 here. So sine of x in degrees has come up not very far. It hasn't reached 1 yet. But sine of x in radians, which is the red line, has repeated itself lots of times, has gone up to 1 and back down to minus 1 lots of times. So you can see here that these are definitely different functions. Now sometimes we want to work backwards. And what I mean by that is if we have our function f of x equals sine x, we want to define a new function called the inverse function of sine of x, which we're going to write as f of minus 1. Now what we want f of minus 1 to do is to say f of minus 1 of x is equal to y, where f of y was equal to x. So an example of this working for sine is that if sine of x is 3/4, that's the same as saying that the inverse sine of 3/4 is x. So x is the angle whose sine is 3/4. Now defining a function like this gives us a small problems, you'll see. Because here we have a graph of sine x, and there's 3/4. So if we look at this, we can see that around about down here, there's an angle whose sine is 3/4, but also over here there's an angle whose sine is 3/4. And there'll be another 2 over here, and loads more over to the far side of the graph, which we can't see. So we need to restrict where we look to find the angle whose sine gives us 3/4. So what we do is we restrict where we define sine. We want to restrict this graph so that every sine value has only one angle giving it. And we can do that, you see, if we cut our graph down so that x goes between -90 and +90. That gives one angle for each sine value. So we say then, if we define our function as f of x equals sine x with domain -90 to 90, then f of x has an inverse. You can use your calculator to work out inverse sines and later inverse cosines and inverse tangents. Inverse sine is sometimes also called arc sine x. Now let's look at cosine x. Again, we can use our circle diagram to see how cosine x and x are related. Like before, we draw a line at x degrees to the horizontal, and this time cos x is the horizontal axis coordinate. We can use this diagram to see how cos x changes as x changes. When x equals 0, cos x is 1. As x increases up to 90, cos x decreases to 0. As x goes up to 180, cos x continues to decrease to -1. As x goes up to 270, cos x increases. As x increases to 360, cos x increases. And at x equals 360, cos x equals 1. As we increase x further, the cycle just repeats itself. We can also see what happens when x is negative. Again, you can see that cosine x must lie between -1 and 1. Here I've got a table already filled in with values of x and cosine x. You can use a calculator to do this. And here's a graph of cosine x that I've created by putting on the values from the table and then using my knowledge from the circle diagram to fill in the rest of the graph. Again, you can see that cosine x is periodic, and again it has periodicity 360, or 2 pi if you're working in radians. Now, like before, we'd like to define an inverse cosine. But again, we have a problem, because there is more than one angle that gives us each cosine value. Unlike before, we can't restrict our graph to minus 90, 90. And that's because there are still more than one angle giving each cosine value. And worse than that, there are some cosine values, i.e. the ones below 0, which don't have an angle at all in this range. So we need to choose a different range. A good range to choose is x between 0 and 180, because as you can see, there is only one angle giving each cosine value here, and every cosine value has an angle to give it. So we can say that if we define f of x equals cosine of x for x between 0 and 180, then f inverse, which is inverse cosine of x, exists. And inverse cosine is sometimes called r cos. Finally, we'll deal with tan x. The circle diagram isn't quite so useful in this case, so we'll go straight to making a table of values for tan x. Now we know that tan x equals sin x over cos x. And we already know something about sines and cosines, so we can use what we know to fill in the values for tan x. When x equals 0, sin x is 0 and cosine x is 1, so tan x must be 0. When x is 45, sin and cos are the same thing, so tan must be 1. When x is 90, cos x is 0. Since any fraction with a 0 denominator is not defined, tan x doesn't have a value at x equals 90. And the same thing applies when x is 270, and any other time when cos x is 0. When x is 135, sin x is 0.71, cos x is minus that, so tan x is minus 1. At x is 180, sin x is 0, cos x is minus 1, so tan x must be 0. At x is 225, sin and cos are the same thing again, so tan x is 1. At x equals 315, sin x is minus 0.71, cos x is plus 0.71, so tan x must be minus 1. And at x equals 360, sin x is 0, cos x is 1, so tan x is 0. Now that we have this table of values, we can use our identity, tan x equals sin x over cos x, to fill in the rest of the graph. I'll write the identity up here. As x goes from 0 to 90, cos x was going down to 0. In fact, cos x gets very, very small as x gets close to 90, whereas sin x just went up to 1. So sin x over cos x gets very, very big. So we can fill in the graph from x is between 0 and 90. It starts at 0, as we saw in our table, and then gets very, very big indeed. When x goes between 90 and 180, sin x is at 1 and goes down to 0. Cos x is negative, but very, very small. So the size of sin x over cos x is very, very big, but because cos is negative, tan x is negative. So just after 90, tan x is right down here, and as x goes to 180, it comes up to 0. When x is between 180 and 270, both sin x and cos x were negative, so tan x is positive. Also, as x got close to 270, cos x became very close to 0, so the size of tan x must get big. So between 180 and 270, x starts off at 0 and then shoots up to very big values when x is near 270. Now between 270 and 360, we have that cos x is positive, but sin x is negative. So tan x must be negative. Again, we're starting off with x being really tiny, so the size of tan x is very, very big. So we're starting down here again and coming up to 0 when x is at 360. Now, since sin x and cos x repeat themselves every 360 degrees, tan x must also repeat itself every 360 degrees. So now we can just fill in the rest of the graph by copying what we've done already. We can do this for negative x too. And this graph will repeat itself however large you let x get, or however negative you get x get. Notice also that tan x repeats itself more often than sin and cos. It repeats itself every 180 degrees. So we say tan x is periodic with periodicity 180. Unlike sin and cos, tan x doesn't have to lie between -1 and 1. If you look at the graph, you can see that tan x can take any value you like, however large or however negative it is. Now we'd like to define an inverse tan as well. Here we need to be twice as careful as we were before, because not only do we have to make sure there's only one angle that gives us each tan value, we have to make sure we don't define the function over a bit where we have an undefined tan function. That is, over a bit where cos x equals 0. A good choice to make is for the graph being between -90 and 90, but not actually including those values. We can't include those values because cos x is 0 there. If we take tan x to be our f of x, and x to be strictly greater than -90 and strictly less than 90, then we can define our inverse tan. And inverse tan of x is sometimes called arctan x.